Have you ever stood at the base of a massive skyscraper, looked all the way up, and just thought, how in the world does that thing not fall over in an earthquake? Well, today we are diving deep into the incredible engineering that keeps these giants standing when the ground itself starts to move.
So really, how does it work? I mean, think about it. You've got a 1,000-foot tower weighing hundreds of thousands of tons, and the solid ground it's built on starts behaving like a wave in the ocean. It seems impossible, right? But it's not about brute strength. It's actually about this really brilliant four-step design philosophy. First, we're going to see how engineers basically forecast the future, figuring out what kind of quake could hit a specific spot. Then we'll get into this wild, counterintuitive idea of designing buildings to bend, not break. After that, we'll look at how they put these designs through a virtual stress test. And finally, we'll talk about the all-important human check that makes sure everything is safe. All right, let's jump in. Okay, part 1, predicting the unpredictable. Now, this whole amazing process, it doesn't start with concrete and steel. No, it starts with data, tons of it, and with truly understanding the specific earthquake risk at the building's exact location on the planet. See, engineers don't just design for some generic made-for-TV big one. Instead, they use a method with a very fancy name, probabilistic seismic hazard analysis, to create a super detailed seismic forecast for that one specific spot. It tells them every possible shaking intensity that site could experience and exactly how likely each one is to happen. It's incredibly precise. And this detailed forecast gives them two really important targets the building has to hit. You can think of them as two completely different final exams the skyscraper has to pass. There's the service level earthquake, and then there's the big one, the maximum considered earthquake. First up is that service level quake. This is the kind of moderate shaking you might expect to see every 40 years or so. And for this test, the goal is simple. The building has to stay open for business. Yeah, maybe you get a few cracked windows or tiles, but structurally, it's fine. People can stay inside, and life pretty much goes on. But then there's the other test, the maximum considered earthquake. This is the absolute worst-case scenario, a really rare, really extreme event. And listen, this is the most important takeaway. The goal here is not to save the building, it's to save the people inside. The skyscraper is actually designed to get seriously damaged. It might even be a total loss afterwards, but it has one job and one job only. Do not collapse. It has to stand standing long enough for everyone to get out safely. So how on earth do you design a building to do that? To sacrifice itself but not collapse? Well, that brings us to part 2, designing to bend, not break. This is the core philosophy of all modern seismic design, and it's probably the opposite of what you'd think. Right, you'd think the best building is a super stiff one, right? One that doesn't move at all. But actually, that would just be brittle and snap like a dry twig. So instead, engineers get clever. They design certain parts of the building to act like structural fuses. These parts are meant to bend and stretch and yield, basically absorbing the earthquake's energy. It's literally the same idea as the crumple zone on your car. At the same time, the most critical parts, like the main columns that hold everything up, are designed to be incredibly strong and never fail. So the fuses sacrifice themselves to protect the really important stuff. Okay, so you have this really clever design. How do you know it actually works? That's where we get to part 3. The virtual stress test. This is where the skyscraper has to fight the earthquake over and over and over again, all before a single piece of steel ever shows up on site. They do this with an insanely realistic computer simulation. They basically build a digital twin of the skyscraper down to the last bolt. Then they can hit this digital model with a virtual earthquake and watch in super slow motion how every single beam and connection bends, stretches, and handles the stress. It's pretty much the world's highest stakes video game. And they don't just do this once. The process is incredibly rigorous. To get the green light, the design has to be tested against at least 11 different earthquake simulations for that worst-case scenario. And each one of those is based on ground-shaking data from a real historical earthquake. This makes sure the design can handle the chaotic, messy, unpredictable reality of a real quake. And this image here gives you a little taste of just how detailed these models get. What you're looking at is basically a digital X-ray of a tiny but absolutely critical connection deep inside a concrete wall. The simulation tests these specific spots to see exactly how they handle the huge, twisting forces of an earthquake, making sure there are absolutely no hidden weak spots anywhere. But you know, even the most powerful computer simulation in the world is only as good as the humans who programmed it. And that brings us to our final, and you could argue most important section, why peer review matters.
This is the essential human safety check on the whole digital process.
See, this whole custom-tailored approach isn't just following a standard one-size-fits-all building code. A standard code is kind of like a recipe book, right? Use this much steel, pour this much concrete. This is different. This is more like a master chef creating a totally new dish from scratch. And before they can serve it, they have to prove to the toughest critics, in this case, the city, that their unique creation is not only amazing, but more importantly, 100% safe.
And that's where the peer review panel comes in. The engineers who design the building have to hand over all their models and all their math to a team of independent, world-class experts. These reviewers then try to poke holes in everything. They challenge every assumption, they question every calculation, and the design team has to answer every question and refine their work until that panel and the city are totally satisfied. It's a critical system of checks and balances that protects all of us.
And honestly, this quote from the official engineering guidelines just says it all perfectly. Most buildings are expected to sustain damage when subjected to strong ground shaking. The goal is life safety, not a damage-proof building. It was never about making an indestructible building. It's about making sure people get to walk away. So the next time you look up at a towering skyscraper, what are you going to see? Will you see a rigid giant trying to stubbornly fight against nature? Or will you see something different? An incredible, engineered marvel designed with amazing flexibility, made to absorb, to adapt, and in a way, to dance with the incredible forces of the earth.